Okay, thanks everyone for taking part in the day one Unconference session. I hope it was good. Although I joked about everyone solving all of the issues, I think they were all really tough problems. So I think just like getting to the grips of them will be a great start. And if they weren't solved, there's 2 more days, or there's 2 more days for Unconference for any other topics that might come up. So we got someone for every group, right? Okay. So are we all right to start at this end with the group for no frame pointers? Okay, no frame pointers group. What did you get up to discussing?
So basically, obviously, one of the problems with profiling user space is knowing how to go through the stack. On x86, a lot of applications are not compiled with frame pointers because it adds overhead. Or sometimes, as you mentioned, there might be some things compiled with frame pointers, but like libraries that are not. So when you try to profile from the kernel or whatnot, you go up into the stack and you go, the only way to get from function to function to function to recreate the stack frame to do those nice pretty flame graphs and everything of the user space, you have to be able to know how, like from the stack, which function called which. And if you don't know how the layout of the stack is, there's it's basically impossible to do that. You just basically stop. So various approaches for solving this. One thing is, I guess perf sometimes will just grab a huge amount of stack and just record that into the ring buffer, like a couple pages worth for every time you do a save. And then at the end, you post-process it and you just kind of scan for functions that are within the stack or use the dwarf information post-processing, because the kernel doesn't have access to the post-processing. But there are ideas maybe using something. Well, one thing I found out today was ARM64 basically almost guarantees the fact that you'll have frame pointers, because the overhead of frame pointers on ARM64 isn't that bad at all. So, and I think someone mentioned that Apple is like enforcing that everything is on like the M1 is. You have to compile to be part of Apple. You have to have frame pointers. So ARM kind of not an issue, but for x86 and I'm sure maybe other architectures it is. And this one thing is maybe if we use sections. So for example, well, frame was mentioned from I guess for C++ exception handlers kind of has that information, or I mentioned using orc, which is what the kernel uses for profiling that obj tool creates. That's a whole nother story. And basically, if you could basically map a section into the kernel, so when you hit it, you could just reference a section to follow the frame pointers up, we might be able to do it. These are just ideas. All of them are very, very difficult to implement. So you have more to add?
Yeah, that's pretty much it. We were discussing some other formats, such as CTF frame, some custom one that my company and I are developing, and in general, trying to see how we can tackle these as a whole in the industry, because it's a big problem, and we don't have a clear solution, right? We have the part that you were mentioning about how to generate that data. You can disassemble the program, the object code, or you can use information provided by the compilers, either the dwarf, unwind the information, or once it lands CTF frame, but then we need to figure out some format that works that can be used in other contexts. So for example, some BPF programs that do profiling or tracing, they need to be able to use that information to unwind the user stack. So we need to think about the layout of that data, but also how are we going to integrate this in the future and make it work. And it's going to take a couple years, but hopefully in some years, frame pointers in user space won't be a problem anymore, or maybe people will start using them. And yeah.
One more constraint that we're trying to also do is not having to recompile the binaries. So whatever's there today, we want to be able to go up and use.
Cool. Thanks.
Before we move on, I want a question for the audience. So people know about inline functions, right? The optimizer likes to inline functions. I discovered, and you're going to know exactly what I'm going to next, I discovered outlined functions. How many people know what outlined functions are? Painful? Painful? Outline functions, yeah, so it's when the compiler can see, oh, the same bit of code is repeated across many functions. I'm going to shove that into another function that has a special name, like 1, 2, 3, 4, 5, outline function. We turn that off in the kernel. But guess what? If you want to work with random arbitrary programs, they're going to have outline functions. So. Yep. Yeah, the outliner can, LLVM loves to do this. So outline functions are a thing. So sorry for interrupting.
No worries. Yeah, I also felt the pain of no frame pointers. You should just wait until you get to Java, where they combine functions at random that happen to do the same thing. Cool. Yeah, so next up we have Ben to feedback from the group that was discussing client and unified client-server tracing.
Hi, I'm Ben. Thanks to Diana for taking great notes. I'm going to skim through them real quick, but try not to spend too much time. So client-server tracing, what we defined it as is a special case of distributed tracing, which we all know and love across your favorite microservices. The tricky part with clients, for example, Android, iOS, web clients, is you can't necessarily trust them. So who gets to make the sampling decision? We talked about things like the client can talk to the server, which can grant it a lease or permission or some sort of token to turn on tracing at its command. Who can make the sampling decision? So if this is made on the client as opposed to the server, are there knobs to decide how fine-grained or coarse is the sampling? We talked about W3C has a standard called trace context that can be used for distributed tracing, but it can also be used for client-server tracing as well. Deciding the beginning and the end of the user's, you can call it a journey or a trace or whatever you want to call it, is a really tricky one. So we had some asides where we talked about speaking the native asynchronous metaphor of the developer. So on Android, you might need to integrate with futures or promises. If you're doing Kotlin, you might need async await or whatever its equivalent is on Kotlin, I forget. And so there are many, many different standards for talking about. Being really mindful of clients' limited resources. So you can't necessarily upload 200 megabytes on the user's metered cellular connection. You can't use up all their battery to upload traces, so you have to be really mindful of that. Clocks are one of the biggest problems. You can't just take a wall clock timestamp like 1:23 a.m. and assume that that has any meaning whatsoever to any servers. Most big companies have a really robust server-side time sync, but nothing on the client. So we talked about really difficult to trace things. So assuming that a single HTTP socket is a single traceable thing is no longer necessarily the case. We have gRPC with streaming, and so you may batching is another example where you may have multiple RPCs batched into one TCP connection. We talked about some other really interesting things about proactively enabling tracing. So this is either the server decides, hey, this response time was way too long. I'm going to return a special header to the client and say, hey, could you retry that idempotent request one more time, but attach this special header to it so that I turn on verbose tracing so that the backend can actually have a hope of figuring out why this request was so bad. Not a bulletproof thing, but it can actually happen. And the most important part is, the actual actionability of these traces. So when something is slow, when you finally have a unified view of the slowness across the client and the server, you don't have the client people pointing fingers at the server people and the server people pointing fingers at the client people, which Premiana knows happens all the time. As soon as you have the actual data and you show people, guess what, you're all clowns and the server is slow and the client is slow, and here is how, then you actually can make some progress. Those were the biggest topics. I don't want to go into a ton more detail, but the notes in the doc in the Discord have the rest. So, yeah,
Cool.
That was a great session.
Great, thanks. And next up, Matthew and Premiana to talk about...
Yes. Okay, I can get started. So the general problem the problem we are trying to solve, what we discussed is, can we have an API for the instrumentation of user space and kernel space so that application developers target that API and the API is agnostic of the specific tracing system that you use, whether it is LTTNG or Yes.
Just a clarification. The API target is for instrumentation of user space.
Right.
Whether we eventually port it to kernel space, we'd see in the future. But the point where it's really relevant for both user space and kernel tracers, right? So you use kernel and user space facilities to trace user space code that has been instrumented.
Right. So we try to say, can we come up with a standard? So we did come up with a standard. It's 10 pages long. I'm going to read it right now. So section 1 of the standard, I'm joking. So, but there are a bunch of parts that we discussed. So
We saw your slides, so
you can, yeah. You see what I'm capable of, yeah. So, and then it was 2 of us, so it's even worse. No, joking aside, okay, there are a bunch of points that we discussed that are interesting. So one part is just the conditional part. So every tracing system is this thing where you want to decide whether you enter the trace point or not. There are mainly 2 philosophies. One philosophy is you dynamically patch the code and you replace the code with some other jumps. The other philosophy is that you have a conditional, and then depending, you change some Boolean and you just jump into that. The point is why we cannot have both. So there is no strong winner. Like one, it's nice for some reasons, but then it's worse for memory. So when you do dynamic patching, it's bad for memory usage and can be bad if you have security restrictions like we have in Android and things like that. But the point is that you can probably have both. You can probably be in a world where the instrumentation point has a trampoline and the trampoline jumps to a place. And then if you can afford patching, you will patch the target of the trampoline. If you cannot afford patching, you will just use that to have a conditional. And then the tracing system can hook up that, like the mechanism that you want. Oh, okay.
No, that's new.
Fight.
Great topic.
The kernel does not have this limitation of not being able to do code patching at all. User space processes have that limitation. Some of them.
There's times where the kernel can't patch. We have two codes pass. One where you can
We need
patch
two
where-
swords here.
No, I was just saying, there's times where the kernel, depending on architectures and whatnot, where you cannot patch. So, we have two paths.
You know that at compile time. So you either compile in the Boolean check of the trace points, or you compile in the ASM GO2. What I propose here is to have an ASM GO2 that is a jump to a trampoline and jump back, followed by a Boolean check. So what you do is, if you cannot do code patching at all in the process, and you know that at runtime, not at compile time, then you use the Boolean to enable. But if you can do code patching, then you can modify the jumps and then skip over the dynamic check. That's the idea. One question over there. Do we have a second microphone?
I've probably lost it somewhere. Oh, it's here at the front.
Right.
Thanks.
Up to the catch box if we throw it in.
Yeah, that was.
Oops, should be high.
I was going to say, we do that in the kernel on ARM64 for alternatives patching, and it adds a huge amount of bloat for all of the out-of-line checks. So
Okay, good, excellent. And the small thing about jumping to another place and not patching the code everywhere. Let's say you are libc and you want to patch in a conditional and change between a jump and an up. So if you patch in most of the libcs in all your processes, they all do copy on write. And you end up having a huge amount of extra pages used in your system. But if you do something like similar to a global offset table, and everything you patch is within a single page or a few pages across your process, then you have a much smaller impact. So that's the interest of having static jumps.
There is another insane possibility.
Microphone, please. Over here.
There is another insane possibility, which is that uprobes already have a mechanism for stuffing a breakpoint into every instance of a given inode across the system. You could stuff something else into every instance of a given inode across the system at a given offset with no copy on write at all. It's horrible, but it seems it would eliminate that problem and give you an entirely different set of problems.
But you might not want to instrument every process in your system. That's
So then there was section 2 of the standard, which is, okay, one, having solved the problem of like the checks and everything, the inline checks and everything, is can we standardize the way we pass the argument? Because often you don't want to trace just like the literal, you want to pass some arguments to the instrumentation point. And then the idea is like we can have something similar to an IOVEC and standardize some data types, because at the end of the day, most tracing system want like int16, int32, and structures and array. And if you cover these and strings, and if you cover these basics, pretty much you covered everything. And then there is a discussion whether we can have variant types or not. That seems like easy to support in any case. But the idea is to say if you know the arguments up front for the instrumentation type, you fill this IOVEC, you pass this to the tracing system, and the tracing system will figure out how to like serialize that and put in their own buffers and everything. The third and last point that we discussed, this is still requires some extra discussion, is what if like the argument that you want to trace is not known statically? What if you want to dynamically attach some information? Imagine things like network logging or heap profiling or compositor tracing, where you don't know upfront how many layers you have. You want to visit some structure and generate dynamically like the data that will make it into the trace. There are some ideas floating around about having some function pointer as part of the instrumentation point and having some API that will allow the tracing system to dynamically give you buffers and the application layer to fill in these buffers and handling this handshake. There was a lot of discussion here. I don't know if we should go into all details because that was long. I don't think that we concluded everything. So like that is probably, if you're interested in the topic, tomorrow we might follow up on this on the next Unconference session, and then I will yield the mic to the next group.
So you present the spec at the next.
Yes, the spec is going to be tomorrow. Yeah.
Yeah, come on.
Yeah. We wasted the 45 minutes. There are a lot of shell,
Ah.
expect there are a lot of shell that it might.
I saw Matthew had some code up. That was okay. So next we have Marcus, who's going to feedback on the
Critical path.
critical path analysis. Thank you.
Brilliant. Good stuff. Thank you. So we started with the round of table kind of state of the art, and I was secretly expecting that somebody would say, just run this with -- magic. That did not happen. So we couldn't get kind of any magic tools. The good thing is that we have all committed, right, to solve this problem by Friday, right? Right, table? Right? Oh, good stuff. So yeah, by Friday, everything will be ready. Done. So a few problems that we're all facing is that it's really hard to calculate the critical path. It's really difficult to know all the dependencies. It requires a deep knowledge of sometimes incredibly complex systems that people don't know how the entire system operate. Crossing boundaries is also getting increasingly more complicated. So crossing from web view to the application, to the server, crossing to neural networks and whatnot, getting traces that crosses all these boundaries is getting very, very complicated. So calculating the critical path across the board, it's something that we just cannot do this.
Google Docs. Sorry.
Yeah, and every single app that we have in here, right? Also, visualizing aggregated traces and calculating critical paths for aggregated traces. If we don't have the basic use case, we don't have a for aggregation either. So it just follows that. However, there's some interesting tools that he mentioned there. A what if tool that you can kind of remove some spans or remove some places and then record. You previously recorded, remove something, and then replay, and then you see what is the impact on the new trace, right? So that was an interesting idea. And there's also a paper that we have looked in my team and his team as well about causal analysis, I think was the... Yeah, there we go. So causal profiling. I believe there will be a link in the doc, I guess. It's an interesting paper. However, it's a very intrusive one where you kind of forcibly introduce latencies or whatnot, and then you run again, and then you see which parts are on the critical path. On our wish list, we started by trying to define what the critical path is. We couldn't get kind of a very crystal clear definition, but something that kind of floated around is that it's a user-centric metric, and by user it means whoever is using your system, not necessarily consumer, that contains all the spans that contribute to that time, and that thing is optimized. And then you can calculate the drag, the slack, and the headroom of all the spans in there. So if you optimize this by this much, how much do you gain on the overall critical path? And conversely, this other thing, if you regress this by this much, how much does it impact the critical path? And across the table, we had a very large spectrum of dependencies. In some systems, they are fully known. In other systems, they are completely unknown. So tracking these dependencies and then instrumenting them is a big challenge on itself. And also externalities. So sometimes you trace your own system, and then for whatever reason, some other process, some antagonistic process, I don't know, decides to bump up the CPU frequency or whatever, and that has an impact on your trace. And if you're not having this holistic view, it's hard to define the critical path for what you're looking. We also talked about accurate simulations. If we had simulations, that would be good, but the simulations need to be accurate, otherwise they're useless. And We also talked about the need for better visualization and reporting tools, and we had great demos for Perfetto and Kernel Shark as well.
Cool.
None of you have talked about using a map. What is the critical part?
Sure.
Thanks.
Give me the neural network by Friday.
Okay, and then finally we have members of the common tracing format group to chat about what they discussed.
Right. Hi. So we looked at tracing formats from two perspectives, which is the first being whether it fits our needs and what's missing. And anyway, let me get started with that. So one of the first things that came out in looking at tracing formats was that.
By the way, just try to so you're not facing your back to the audience.
Right. Okay.
So you do this way, so it's
Sure. Thank you. Most tracing formats today they are like tree oriented, but what we actually need in some cases is to be able to represent DAGs. Example will be something like streaming response from a server. You have something a request that comes in and a sequence of responses. So we want to be able to capture that kind of semantics. We looked at CTF, common trace format, and that was we looked at it as an exemplar of what we kind of want, which is like a self-describing format and dynamically extensible. And there was discussion about whether CTF we could generate code from it, whether we could do things like cookie propagation, so that's part of the way to recover a DAG from a trace. We looked at other things, like how do you name parts of your trace to be able to treat them as values. The reason is you might want to do a diff between two traces. And when you do things like diffing traces, you want to ignore certain fields which are transient, ephemeral, things like thread IDs. So it would be nice to be able to mark that in the trace definition somewhere. So that comes to the point of how do you describe all of these things so that you can have binary data coming out and different tools looking at a description of the data, knowing what to do with it, how do you encode higher level semantics. So that led to the discussion of standard types. We'd like to be able to say things like, this is a POSIX thread ID and in the trace. And so tools then would know that this has to be treated with some kind of special semantic, whether it's a thread ID, not an integer. So if some analysis tries to add or multiply two thread IDs, then at some higher level you can reject that kind of analysis. We also discussed the problem of timestamps, and how do you align clocks, especially from.
You're about to fall off the stage.
No problem. I can manage that, sir.
I'm getting nervous.
No issues. Timestamps, aligning clocks. There's a problem of sources having two different types of resolutions. So you could have a time source which has nanosecond resolution, and another one which has, let's say, millisecond resolution, and then now all of a sudden you have events all being collapsed when you display things on your trace, and so it looks like lots of stuff happened simultaneously when they actually didn't. So then again, we looked at, when you're talking about trace formats, what's the actual question here, and what we looked at what are the questions answerable from a given trace. So focusing on tracing from trying to say, okay, what's the question we're trying to answer here? That led to a discussion about, the different views you have given a trace. For example, somebody doing kernel scheduler development would want data at a completely different granularity and visibility compared to an application developer who'd be more interested in a more top-level view. But you also want the ability to go down deep if you need that. So this is what we looked at. This was a
Cool.
Discussion. Okay, thank you. And if you have any questions then about CTF, and I think I'd hand it to my colleague Jeremy from FECUS.
Cool. Any questions? Otherwise, big thank you to everyone who stood up feedback on the session. Sorry, was there a question?